Welcome back to ECE 442-542, the day before or the class period before exam number 3. We will have a review session tonight, and this lecture and the review session will attempt to be posted. Did I start? We will continue as if nothing happened. Well, today we have two more root locus rules that I want to cover, and they can be on the exam. They're fair game, but we'll see in terms of, I think they help you better understand what you're doing or more quickly sketching the root loci. And we'll do that via some examples. Very quickly, the process for exam number 3 should be consistent with what you've been doing all semester. Front and back of 3 sheets of notes now. You will have a calculator, a writing instrument, no cell phones, no computer, no textbooks, and no communicating during the exam. That's the process. I'm going to simply state these rules, and then we will go through them via examples. And I'll make the screen a little bit smaller. You have young eyes, you can see this. This will be posted, hopefully, and you don't necessarily have to write it down. But the rule number 4, I'm sort of assuming we've already talked about the 3 rules, or those 3 rules you now know. We'll start with rule 4, and these are basically about guidelines. Guidelines that help you sketch the branches of the root locus that go off to infinite zeros. And these are called asymptote lines. You're going to have many of these lines. You'll have as many of these lines as you have infinite zeros. And where they're centered, we call that their centroid, where all of these lines originate on the real line. That's their centroid. You can compute that by simply summing up all of the poles, subtracting the sum of all of the zeros, and dividing by the pole zero excess. A lot of times I'll call that P minus Z. Today I just decided I'll call it PZ sub E, pole zero excess. The angles themselves can be found from this expression, and I usually just concentrate on the first angle, the fundamental angle, which is 180 divided by the pole zero excess. We've already looked at these asymptote lines when we had a pole zero excess of 2. When we had a pole zero excess of 2, we have 2 zeros at infinity, and this asymptote angle, the fundamental angle, becomes 180 divided by 2, or 90 degrees. If we have 3 zeros at infinity, 3 more poles than zeros, then we're taking 180 divided by 3, and these asymptote angle, the first one's going off at 60 degrees. Basically, these asymptotes split your z-plane equally. They cut it up into pieces. And when we had the 2, one was at 90, the other was at minus 90, or it was at 90 and 270. And that cuts the plane in half. If we had 3 infinite zeros, it would cut it into 3 pieces of this pie, so to speak. One's at 60, one's at 180, and the other's at 300. And that equally splits this pie in 3 different pieces. And the centroid is there. And here's just an example of that. And again, we'll go through an example of this, but this is a picture to get you thinking about what's happening. In that picture, what's the pole zero excess? I'm hearing 2, I'm hearing 3. Do I have a 4? You're looking at how many x's you have. That's the number of poles, which is 3. How many finite zeros do you have? There are no open zeros or open circles, so your pole zero excess is 3, and that angle that I've indicated here, this phi sub A, is supposed to be 60 degrees. And I'm just sketching these quickly. The other asymptote angle, which you don't really see, is essentially buried underneath the negative real axis. It's at 180 degrees. And the other asymptote is going off at 300 degrees, or minus 60 degrees. So that the angle between these asymptotes is 120, 120, and 120. It's subdividing that z-plane into 3 equal parts. We'll look at that, but these lines are simply asymptote lines. The branches asymptotically approach those lines. Sometimes they live right on them, but most of the time they're asymptotes that the branches approach as you increase the gain k. That's rule number 4. How do we sketch those asymptote lines, and how many of them are there? Rule number 5 is really only going to be in play when you have complex poles or zeros. And by that I'm meaning poles or zeros that have non-zero imaginary parts. They're off the real line. So if you have 2 poles that are complex conjugates, then you will have rule number 5. And this is really just asking or answering the question, where are my branches? How are they leaving the poles, these complex poles? Those are the angles of departure. Or if those poles were instead zeros somewhere, how are my branches approaching those zeros? Those are angles of approach, or angles of arrival angles. These, indicated in this example sketch, are angles of departure. And those, again, are measured relative to this horizontal positive real line. And in this case, phi sub d is, where does that branch initially, in what direction, angle-wise, is that branch leaving this pole in the first quadrant? And that's, what, 135 degrees, something like that. That's what you would calculate for phi sub d, based on the phase angle condition. And again, we're going to look at some examples of that. Let's start with a little insight behind rule number 4. Whoops. Suppose somebody has the following picture, and they say, okay, I have a pole there, a zero there, and a pole there. And you can see that you do have a pole zero excess. And you want to know, oh, where are my asymptotes going to be located? Or where can I sketch those? And asymptotes are representing something that's happening as you get really, really far away. These are asymptotic lines. If that's the case, what does this pattern, this pole zero pattern, far away from this finite region of the z-plane, maybe you could say in a galaxy, far, far away, right? Make this into some interesting story. But far away, what does this or that pole zero pattern look like? If you went a long distance away in the z-plane and you looked back at this local region, what would it look like? That's really the idea behind these asymptotes. If you went way away from this, do you agree that it might just look like a couple of poles centered somewhere? It'll have some centered by their relative weights or their relative locations. They will have a centroid. They will have some spot on the real line that they're centered. A long way away from this pattern. Whoops, let me go ahead and try to be consistent. You might see or really feel something like that. Those are supposed to be right on top of each other, and they're on the real line, although I haven't drawn them that way, but I'm trying to indicate that there are two. These will be located at what we're calling the centroid, sigma sub A. And there's two of them. There's two poles. Because if you look at this diagram, you had 3 poles minus a 0, so you effectively have a net 2 poles when you look back on this spot way away from where they're actually located. It looks like this, and they're centered at sigma sub A. And if we said, is this, or what do we know about which locations now belong to the root locus? If we went up here and we said, does that point belong to the root locus, what would you tell me for this picture? Is that red dot, does it belong to the root locus? And how do you know? Yes or no? And this could be an exam question. I could just put down 2 or 3 X's and draw a point and say, is that point, does it belong to the root locus? You wouldn't have to sketch the root locus. You could just do a calculation. And what would that calculation be? You need to see if the angles contributed by all of your singularities, or your poles and zeros, if they sum to minus 180 degrees. In this case, if you look at that, the angle from this pole to that point is that angle. That's 90 degrees. This one has exactly the same angle if it looked up to that dot. So you have 2 poles contributing each 90 degrees. In other words, we're looking at the angle of this expression. Z minus sigma sub A downstairs, and we have 2 of them. We're looking at the angle of that, and we know that that needs to equal minus 180 degrees. If that's what we have, then I hope that you can see that each of those angles, we could say, oh, we have an angle due to the first pole, and we have an angle due to the second pole. That's the left-hand side, and we're saying that equals minus 180. And both of those poles experience the same angle. They're right on top of each other. So we could have said that's minus 2 theta sub P1 is equal to minus 180. We can divide the minus 2 out, and we can call that theta sub P really the asymptote angle. So this theta sub P1 is really what we were calling theta sub A, which is now 90 degrees. That's sort of the idea behind this rule number 4. We're simply going a long distance away and saying what would have happened, and then we really can just apply these formulas. And the formula give us the centroid and the angles. The centroid, sigma sub A, and I'm trying to help those of you that are texting. You can just say RL. So that's the root locus, the centroid of the root locus asymptotes, and this is really the real line point where the asymptotes are centered. And to find that, we simply sum all of our poles. We subtract from that all of our zeros, and we divide by this integer given by the pole zero excess. That's sigma sub A. That's where those asymptotes all meet on the real line. That's sigma sub A. Their angle, which I'm just lumping as phi sub A, if you want all of them, then you need to iterate through or crunch through all the different integers in. Again, we divide by the pole zero excess. And n is going to be either 0, 1, 2, all the way up to 1 less than the pole zero excess. And that will give you all of the different angles. 60, 180, 300 if your pole zero excess is 3. If your pole zero excess is 2, it's 90 and 270. If your pole zero excess is 4, now your fundamental angle is 180 divided by 4, or 90 divided by 2, or 45. So it's at 45, 135, 225, and 315. If you split the 360 into 4 little parts, each separated by 90 degrees. And the branches of your root locus are going to approach those asymptotes. All right, let's go through an example. That was sort of the background behind this. Suppose that I now tell you that g of z is equal to 2 over z plus 1/2 z minus 3/4 and z minus 1. And there's all sorts of things I could start asking you about that g of z on the exam or today. Is it stable? Marginally. We have that poor guy out there on the unit circle at 1. But yes, you could say that's marginally stable. If you excited this with a step, that one would go unbounded with time, that mode at z equal 1. So that's why it's called marginally stable. I really wouldn't want to build this and try to live with it. I would probably put some feedback on it and then see if I could live with it. But what we want to do now is sketch the root locus for this g of z. And the first thing that you might be doing, obviously, once I say root locus, you're playing the game and you put down your x's and o's. How many o's do you have? And unfortunately, I picked a numerator of 2. That's not a z, that's a 2. How many zeros do you have? Finite. 0. You do not have any, and you have 3 poles. That says then that our pole zero excess which I said, oh, today let's call it pz sub e, is 3. Our asymptote angles are our phi sub a, which are 2n plus 1, and again, n is just an integer, assuming values of 0, 1, up to 2 in this case. And we're divided, well, let me go ahead and just say for now, since that's the generic formula, still, let's just say that's pz sub e. Or phi sub a is now n equals 0 is 180 degrees divided by 3. Then we plug in n of 1, and we say 3 times 180, which is 540 divided by 3. And then we have 5 times 180, which is actually 900, and we divide that by 3 so that our angles of our asymptotes are 60, 180, and 300 degrees. Those are our asymptote angles. And essentially, if you thought of this as, oh, I have angles 60, 180, and 300, you have to figure out where do I pin that on the real line. Otherwise, it messes you up. You need to know where to pin that, and that's what your centroid tells you. Your centroid now sigma sub a, I sum up all of my poles. I had a pole at minus 1/2. That's the z plus 1/2 factor. I have another pole at 3/4 plus 3/4, and I have another pole at 1. I didn't have any zeros. I'll go ahead and show that. I'm subtracting nothing, and I'm dividing by the pole 0 excess. So I have 1/4 more than 1 sitting in there, or something a little bit bigger, or I'm sorry, a little bit less than 1/2 for my centroid of those two lines. And this, if you compute that, is about 4.2. That's where I am between 0 and 1 with these three asymptote angles at 60, 180, and 300. And now I can sketch my root locus maybe a little bit more quickly or more effectively. I had a pole at minus 1/2. I had a pole at 1, and I had another pole at 3/4. What I've just learned is that I now have a centroid, sigma sub a, right there. And leaving that are my asymptotes. And if I could sketch something at 60 degrees and minus 60 degrees, that would be my asymptotes. That means branches of my root locus need to approach those asymptotes. How are they going to start getting there? Now you're applying rule 1 and 2, right? Which line segment which segment of the real line belongs to the root locus? From 1 to infinity, is that on the root locus? From 3/4 to 1, is that on the root locus? From minus 1/2 to 3/4? From minus 1/2 to minus infinity. And that one's going off along one of the asymptotes. I could have sketched a black dashed line at 180. That's also possible, but it would be buried underneath the green line going off to minus infinity, and so I didn't do that. But now we could compute the breakaway, which is going to happen somewhere between 3/4 and 1. But if we're in a hurry, we just say, you know what? It's breaking away somewhere between there, and there's my root locus. You're finished. Maybe not. Now maybe you want to know something a little bit more, but you have a pretty good feel for what's going on. How would I find, as a review, how would I find that point where they break away? And these you should just be able to quickly do on the exam on Wednesday. Fine, I might ask you, where's the breakaway point? I might ask you something easy and say, circle the real line segment where the breakaway might occur, or where the breakaways might occur. And there you're just circling. If I ask you to do that, and here I might say, highlight in yellow the breakaway segment, and that would be what you would do. You won't have a highlighter. You don't have to go out and buy highlighters, but I might say circle. I might ask you to box with a rectangular box the region where you might have a reentry point. Would you have a box on this sketch? No, you don't have a reentry place where the root locus is coming back. It's reentering the real line. So you wouldn't have a rectangular box. Is that clear? For what you... Now, how do we find the breakaway point in that highlighted region? What do we use? What condition? The yes-no condition, the fail-safe condition. What conditions do we have for the root locus? We actually have two. We have a magnitude condition. What's our other condition? Phase. So we have the magnitude condition and the phase condition, and in fact, we could use the magnitude condition for this one to find our expression for the gain, K. K is now going to be all of these pole distances divided by, let's say, the scalar and our zero lengths. And any point on the root locus, if z belongs to the root locus, we could find the gain k to get us to that point by substituting that z value into this expression. We're now using this expression, let's say numerically, to plot this curve between z values of 3/4 and 1, and we're trying to find where's that k value reach a relative maximum. Where k reaches a relative maximum is the breakaway point. You don't have to do calculus. You can do this numerically, especially when you have a third order, and if you had a fourth order and maybe a second order numerator, now you've got a quotient of z's. Might get kind of tedious to differentiate that. So you could do this, and if you did this numerically, you might find, well, you will find that you have a relative max of k at a z value of 0.881. And if you now plug that z value in, you'll actually find the k at that z value. You don't have to crank up the gain very much to get you to the breakaway point. Just a little bit more than 1%. 0.0, well, it's not really a percent. The gain k of 0.01. 0.011 gets you to where those two meet on the real line. Questions on that? Now, if you were thinking about this, and I ask you, find the range of K for stability, do you know how you might approach that problem? If I ask you, draw me a picture or tell me a story, if I didn't tell you to numerically find or to find the range of K for stability, what are you really looking at? Once you have this picture, can you get an intuitive feel for what's governing stability in this root locus? You might want to draw a unit circle. So I guess I should have included on the exam process, you can bring in dividers and a compass if you want. Just don't hurt yourself with the compass or the dividers. You probably don't even know what dividers are. Anybody have a mechanical drawing class that wasn't computer-based? Probably not, huh? Oh boy, I'm dating myself. Dividers. If you had a mean instructor, he'd throw them at you. And they would stick in the wall if they didn't stick in you. Old school. Aren't you glad we don't have dividers? Pardon? Brutal. Yes, it was brutal. So we sketch a unit circle, which probably isn't going to be very unit, but oh. Well, you get the idea. But if you're telling the story, ooh, that's pretty ugly, unit circle, but now that you've sketched this unit circle, what does that tell you? This is with just a constant gain, isn't it? This red line is for a controller that consists only of a constant gain in a unity feedback configuration, and it produces these closed loop poles. As I crank up the gain K to 0.011, I get these two to come together and meet at 0.88. And then what about this guy here? How many branches of the root locus do I have? How many root locus branches do I have? This could be a question on the exam. Pardon? The number of poles. It's not a hard question, is it? So how many branches do I have? You're avoiding the question. 3, right? Even though I might just have 2 line segments, I have 3 branches because I have 2 branches on that single line segment. And if you counted just the tails, you had 3 branches, didn't you? What you need to worry about is you want all 3 of those branches to be living inside the unit circle simultaneously for closed loop stability. The question then that you need to ask is when K gets up to a big value of 0.011, which brings these two together, has this guy already zipped outside the unit circle? Could you check that very easily? Could I ask you to find the gain K that would drive one of your poles to Z equal -1? Can you calculate that? This is another question for the exam. You can go back to this formula. Boy, thank goodness. Whoops, what happened to it? Oh, there it is. I slid up to go back to my, sorry. I'm so excited I don't know whether to go up or down. Here's K. Now we can substitute into that a value of z equal minus 1. And we end up with 2 7/4, 1/2, and 2. Or a k value of 7/8. Or that's equal to this 0.875, which is bigger than 0.011, isn't it? Which tells us what? Are we stable at 0.011 for k? And that one's a yes or no. You don't even need a three-sided coin for that one. Now, at k equal to 0.011, this guy, we didn't calculate what it was, but we could. How could we calculate the closed-loop poles at a gain k of 0.011? Another question, easier question. Are all of your poles, closed-loop poles, real when the gain k is 0.011? So this one's another two-sided coin, a yes-no coin. Yes or no? How many say yes? How many say no? How many aren't saying? What, it's a trick question? Oh, you didn't hear the question. Well, I'll turn up the volume. So now we're asking for k of 0.011, are all three of our closed-loop poles real? For this case, just for this case. We're assuming that these two are real. They're hitting right at 0.011. We just learned that it takes a gain of where'd it go? 0.875 to get this one all the way there. So at 0.011, it's maybe right here. These two are right there. They're all three real, aren't they? Does everybody see that? Sorry for those of you playing along at home, you didn't see those fingers, did you? Pointing to the three spots. But you can imagine where they are. The one at -1/2 is approaching -1, but it's a long way from -1 at that gain of 0.011. So what's your range of stability on K? Have we found it yet? You could evaluate the closed-loop poles at that gain, 0.875, and find out where your poles were. I might say, okay, here's this guy. I'm going to call that a box. And maybe these guys have moved out there when k is 0.875. And that gain may be too big. Those that were near 1 have already zipped outside the unit circle. Meaning, we may want to back off on the gain from a value of 0.875 down to a value that gets you to those triangles right here where your root locus just intersects the unit circle. And if you were doing this by hand, that's why you have your dividers. If this is sketched accurately or pretty close, you can now figure out where that triangle is. And if this was sketched better, you might say, oh, that's at about, well, this one's maybe a little, the one in the fourth quadrant might be a little better. It's maybe at 0.9 and a real part of 0.4. And you could say, oh, maybe that's the value of z where I just escaped the unit circle. And you could, even though it may not be on the root locus, you could plug that value in here for k just to get a feel for how big is k close to that boundary. You're trying to get a sort of a intuitive feel for the gain for stability. And you have now eyeballed that from this root locus, and you now can say, oh, let's just say that the gain k, let's say k at delta is approximately, because we don't know exactly, we didn't find it. And we could check if it was on the root locus, but let's just say that we're assuming this is, what did I say before, maybe? Ugh, did I ever say? Maybe we say that z delta is 0.9 plus j 0.4, boy, I was really getting specific, 0.43. And if you do that calculation, you can plug in a complex number for z, because you're taking the absolute, you're just taking the magnitude of that complex number, multiplying those together, and if you had dividers, you could set your dividers at that triangle and the pole at 1, measure it, triangle, and at 0.75, measure that length, and the other pole, which was at 1/2 in that triangle, and measure that. Those are your lengths. Multiply them together, divide by 2, and you get this approximate value for k, and it ends up being quite a bit less than 0.875, 0.1472. And if you looked at the roots, where are your closed loop poles, or what governs those? Right? That's your denominator of your closed loop transfer function. And in terms of what we have, we now have 1 plus k, and this was 2, z minus 1, z minus 3/4, and z plus 1/2 equal to 0. And we need the numerator of that, so that will give us our characteristic equation, which is the governing equation for the closed loop poles. And if you plug that into C0 on your calculator, for example, with k equal to 0.14, whatever I just said, 2, we end up with the closed loop poles being at 0.94 plus and minus j 0.42 and minus 0.631. Is that stable? If not, or if you don't know, what would you do to this to check stability? You just find the magnitude of those complex guys. So if you do the magnitude of that complex number, in fact I did, this ends up being 1.03. This one's pretty easy. I can do that magnitude without too much. That's 0.63. So that's a little bit too big. But it was just an eyeball guess. It got us pretty close, didn't it, to a stable location or a value for k. So we need to not crank up the gain quite that much. If we back off on the gain, and here you could just sort of guess a little bit, but if you found, instead of 0.147, 0.11, this is a good value. It makes it just barely stable. So your range for stability on k is now between 0, and 0.11. Are we going to be happy with the behavior of that closed loop system if we pick a K in that range? It's a subjective question, isn't it? It really depends on your system. If you picked a gain K of 0.011, you now know that you would be all three real poles. And maybe that's what you would try. What's the settling time for that choice? It's obviously stable. Now I ask you, what's the settling time for this system on the exam? I say, oh, for this gain K, what's the settling time? Find the poles. We've already found the poles, actually. That gain corresponded to what location? That was the breakaway, wasn't it? So we know the poles are at 0.88. And we know the other one is here somewhere. It's not quite 0.88 negative. So which poles are going to dominate the behavior? Pardon? The long duration poles. Which ones are long duration? We have three poles. One's at 0.88, one's at 0.88, because they are right on top of each other, and the other one's, let's say, at some value, minus 0.7. 0.88, right? Because they have a bigger magnitude. They're closer to the unit circle. Those are the slower poles. Those are the dominant poles. So now we pick a dominant pole. Oh, I'll get really precise. 0.881. What's the settling time? What are you doing now? You're going from Z delta to transient specs or transient performance. What's the settling time? Can you get it from this? And what does this tell us? This gives us our radius, doesn't it? And we know the relationship between radius and settling time for a discrete time system. For 1% settling time. We don't even know what the sample period is, do we? We weren't told that. Somebody just gave us a G of Z. They'd already given us the Z transform. They didn't tell us what the sample period, but we can tell them how many sample periods it's going to take to settle. So if we solve for n sub s with a little logarithm calculation, n sub s is now minus 2 over log base 10 of r. System settles in how many sample periods? 37. That may or may not be fast enough. What's our steady state error due to a constant input for this system? Somebody put in a constant input to a reference in our closed loop configuration. We have a gain of 0.011. What's our steady state error? Pardon? You could calculate it, But actually knowing what we know about this particular system, wow, where did it go? We have an open loop pole at z equal to 1. That's going to give us a type 1 system. It's going to have zero error due to constant inputs. As long as everything is stable, as long as our closed loop system is stable, we can just say that. It's a type 1 system. The steady state error is 0 due to any constant input. As long as your closed loop system is stable, and it is. Our slowest pole was at 0.881. You could go and compute the DC gain of your closed loop transfer function and see that it's 1 and say, oh, good, I have no error due to a constant. You don't even have to do that. Now that may be too slow, 37 sample periods. You may want to speed it up. Well, we'll learn how. Question. A type 1 system, anybody want to help? Anyone brave enough to remember what that was? System type depends on your plant and controller combination. In this class, that's the loop gain. The type depends on how many poles in that pole or plant controller combination are at z equal to 1. How many poles do you have at z equal to 1? That's your type. That had one pole at z equal to 1. It's a type 1. If it had 0 poles at z equal to 1 and you still made it stable, that's a type 0 system, and you're going to have a finite steady state error for a type 0 system. A type 2 system allows you actually 0 error to a ramp input and a bounded error for a parabolic input. That's a type 2, which means you had 2 poles at z equal to 1 in your plant controller combination. -1 isn't going to work for us. So the question was, what about -1? That's not a good point in terms of steady state accuracy. All right. Well, if this is too slow, we would design a PID controller, and I'll leave that for the exam since we've covered that. Not. So on the final, we'll worry about PID controllers. But for today, let's move on to the last rule, rule number 5. Too slow. We wouldn't need to buy a vowel. We would just guess a D, wouldn't we? We would just add a D. We have a PID now, proportional integral and derivative controller, and we'll learn what that means next week. But for now, let's go with rule number 5, and this is angle of departure or angle of arrival. And this really only is an issue when you have complex poles or zeros. And when I say in the system, I'm meaning the open loop system, which is the original plant or the controller. Let's just look at an example. G of z, let's say, is 2 z minus 1/2 over z minus 1 squared plus 1/2 squared. Now I want to sketch the root locus for that. Do you know, when I say root locus, we've started a new game. Can you at least put some zeros and x's down to get a half a point out of 25? Right? That's if you get all the x's and o's. If you just get one, you might get an eighth of a half out of 25. Better hope for better partial credit than that. Put me in a good mood to grade. So, where do we put these x's and o's? Answer the easy one first. What's easy to put down? You have an O at 1/2, don't you? A 0 at 1/2. Positive 1/2. That's the value of z that causes that numerator to vanish. The finite value of z occurs at z equal to 1/2. There's my 0. My poles is at 1 plus and minus j 1/2, isn't it? Written in that way. So I now just go up here to 1 and up and down plus and minus j 1/2. Now, can you do anything initially before you, well, what's the next step? What's your pole 0 excess? 1. So do you have an asymptote? Do you have an infinite 0? Your pole 0 excess is 1. You have an infinite 0 of 1. You have an asymptote at 180 divided by 1. So you have an asymptote going off to minus infinity. It doesn't matter where the centroid is. It's going off at minus infinity. Do you have a portion of the root locus to the right of that 0 at 1/2? If you ask for the phase at 1, what's the phase at 1? Don't worry about your off-axis poles and zeros. They cancel each other out, so you don't need to worry about them in figuring out, do I have an odd number, do I have an even number to the right? Don't worry about the ones that are off-axis. They cancel each other out. Is the point 1 on the root locus? Is the angle to this point minus 180? I look at it from this 0, that's the only thing on the real line, and that angle is 0. That's not 180, is it? What if I come over here to minus 1? And I look to that point, minus 1, from all the points on the real line. There's only one. It's odd. I have to look 180 degrees. And that's consistent with my pole 0 excess. So I have 1 0 at infinity for a big enough gain k. Now what happens? How many branches do I have? How many root locus branches do I have? I have 2 poles, I have 2 branches. Now I'm asking for, how do these, they start on the x's with k equals 0. As I crank up k to an epsilon value, where do I start going? In what direction do I leave those poles? And that's what this whole Rule 5 is going to tell us. So what you do is essentially what we're doing is we're picking an arbitrary point right there, and that's an epsilon distance away from that pole. See how small that is? So you can see it. But now I am interested in, so if that was an epsilon away, I'm interested, is that point, I want to make that point live on the root locus. So that this angle right here is phi sub d. That's my departure angle. I know that if that point is on the root locus, all of the poles and zeros angles need to algebraically sum up to minus 180 if that point is on the root locus. And what does this say? This formula now says I have all of the angles of the zeros, and I only have one zero. That's the angle of that. And I add all of those up with positive signs since they're upstairs. They're in the numerator. And I subtract from that all of my pole angles. I have a pole at minus 1 minus j1 half. Which pole was that? Up or down? That's the one up, isn't it? Z of 1 plus j1 half will make that vanish. So that's the upper complex pole, and I have its twin down below, Z minus 1 plus j1 half. Does everybody see what I'm doing? So I now have this angle, and if that's epsilon close, it's basically right on top of that x, so I can just find this as theta sub z. The angle from this pole, this open loop pole, up to that epsilon close, let me call that theta sub p, let me call it theta sub p2. And if it's right on top of that x, what's theta sub p sub 2? $90 degrees, isn't it? It just turned a right angle. And if I've done my, that's why I put these where I put them, I'm moving over 1/2 and up 1/2. What's the angle for theta sub z? So now from this, from this formula, I now have theta sub z minus, and I'm calling this angle my departure angle, phi sub d, and this one I was calling theta sub p sub 2. And these have to equal minus 180 degrees to be on the root locus. Is everybody okay with that formula? Theta sub z was 45 degrees. I walk over 1/2 and up 1/2. Theta sub d, I don't know what that is. That's why I'm calculating that. That's some angle from the horizontal real line associated with that pole in the first quadrant, that complex pole. And what was theta sub p sub 2? And I'm subtracting that. I go from this pole downstairs and look straight up, which is an angle of 90 degrees. And those algebraically, if they're on the root locus, those angles have to algebraically sum to minus 180. And now I can solve for the departure angle, phi sub d. Phi sub d is now 180 plus 45 minus 90 degrees. Is that right? So now I have 180 minus 45, or 135 degrees. That now tells me phi sub d, infinitesimally close to that pole, is moving away. The branch is moving away at an angle of 135 degrees. So I go 90 and 45 degrees more, and now I know the angle that I'm departing from. It's going up at 45 degrees from that point. Is that clear? And whatever I sketch upstairs in the positive complex half of the z-plane, I do its mirror image below. So if that one's going up at 135, this one is going down at minus 135, if you wanted to think of it that way. So this one now is doing this. Can we figure out how to connect the dots or connect the segments? What else can we find? You know what? This one's not too difficult, actually, if you brought your compass. Because this is a two-pole 1-0 configuration, which means that they are living on a circle of radius equal to the distance from that 0 as the center up to that pole. This only works when you have two poles and a 0. If you had another pole somewhere or another 0, don't be doing this. If you had other singularities around, and let's say you still had this segment from 1/2 to minus infinity in play, could you find any more information on that on that z-plane that would help you? Now, if I'm circling my breakaway segments and I'm boxing my reentry segments, do I have either of those in this diagram? I better have a reentry, hadn't I? Because these two branches start off the real line, and eventually they're going to have to end up on this real line. One's going to have to end on the finite 0. The other one's going to march off to that infinite 0. We have two branches on that red shaded real line that's drawn there. And I just said in this case, with two poles and a 0, we could get our compass out and sketch the circle. That circle now has a radius of the square root of 2 times 1/2, or the square root of 2 over 2, or 0.707. You could set your compass to 0.707 and sketch that. I'm getting really nervous now. But that should be about 0.2, right? So, oh, just think that's just nice, please. Do you see what's happening? Now you know where it's re-entering the real line. These are taking off at those respective angles. They meet right here. Could you find the gain that would get you to this point? After they reach that place and hit each other, they split off. They live on the real line. One goes to that 0 at 1/2. The other one goes off to minus infinity. Do you initially start stable in this system? Yes or no? Why not? Your poles have a magnitude bigger than 1, don't they? They were at 1 plus j 1/2. That's bigger than 1 in magnitude. So you're not starting stable. You have to crank this up a little bit to get where? Now you need to sketch your unit circle again. Man. All right, give me a minute. Give me a, I'll fudge this. I'll come from -1 and stretch it out. But do you get the idea? Now you want to know what gets you to that point. We've just learned what happens at that cloud. That's where they re-enter, and this is where they go unstable again. And you could compute the gain to get you to those three places. Graphically, might be the quickest if you sketch these somewhat reasonably accurate with maybe some grid paper. Do you see what I'm saying? To get the magnitude of the gain, this was our system. We now would say our gain K is going to be the length from that pole to z minus 1/2. That's our gain formula. And now, if we went to the cloud, cloud computing, never mind. But the cloud is where we would re-enter. That's our re-entry point, and we could find the gain to get us to that point. What is that? Well, we would measure from this pole. This is why you come to class, because you're measuring from this pole to that cloud. You could measure that with a ruler or with your dividers, that distance. That's this length right there. And you can numerically compute that. The z is at minus 0.2 because it was 0.707 from 1/2. So it's at minus, and so you'd need to use the right algebraic sign. That's at minus 0.207. And you could compute that gain to get you to the gain for re-entry. Is that clear? You could compute the gain to get you to the triangle by measuring the distance from here to there, from here to there, and from there to there. Those three lengths put into this formula, the first one here, the second one there, the third one there, and keeping track of that 2, put all those together, multiplying and dividing properly, and there's your gain K to get you to the triangle. Question? So now if you had this K value, you could sketch this K. It's easier maybe to sketch it, but what are you wanting to do? Now, if you wanted to find the relative, what's going to happen here at the cloud? A relative maximum or a relative minimum of K? It's a re-entry, isn't it? So that's a relative minimum. Because if you think about it, when you hit when you hit this re-entry point, when you hit the cloud, what happens beyond that point? You have to increase K, don't you? So this point, that cloud, is a relative minimum. For any K bigger, you're further away from that cloud. If you now looked at, so what values of K, well, you already know where the re-entry is, but if you didn't know, you would start evaluating this K formula at, let's say, z equals 0 to maybe z equal minus 2, and say, is there a relative minimum in that region? And you're going to find that indeed you do have a relative minimum at minus 0.207. Is that making sense? Yes. It's a relative minimum on the real axis, correct. You just use z's on the real line. You can evaluate, if somebody said, I want to know what's going to get me, I'm running out of shapes here, I'm shape challenged. So let me do, Oh, that looks like two O's. But that was supposed to be a dog bone. So now we have a dog bone. Somebody wants to know, what's the gain to get me to that bone? Especially your dog, right? What's the gain to get me to that bone? How do you find to get to that dog bone? How do you compute the gain? Pardon? Graphically would be the easiest, wouldn't it? That's what these dividers are for. You would simply measure the distance from this hole to that bone. The straight line distance. You would measure from here to there, and from, I can't show it, from the 0 there, and don't forget your 2. But you have those 3 distances and the 2, and that's going to give you your k to get you to the dog bone. If your root locus is drawn accurately, you can find the gain k pretty easily, graphically. Questions on that? I think I'm out of bones and out of time. We'll pick up somewhere talking about an exam review in a minute.